Hi there, welcome to this video, which I hope will be useful in helping you prepare for your AP Maths Paper 1. Just in terms of how to watch this video, just to emphasize that this is simply a recap of topics that we've covered, and I would encourage you to do past papers as well. So watching the video is no substitute for past papers. I'd also encourage you to watch it actively, and by that I mean that you should pause it from time to time and think about the solutions to the questions yourself rather than just passively watching it. Just remember that in AP Maths Paper 1, and in fact in Paper 2, just 36 seconds per mark. So it's really quite tight, and you need to use your reading time really well. During the reading time, you need to target the low-hanging fruit. You need to target those questions that you're easily going to be able to do. Equally, you need to be able to identify questions that you really don't have a clue about, possibly, hopefully not, but and you need to leave those for the end. Get some marks behind you right up front. Use your calculator to good effect. So wherever possible, use your calculator. If it's a question of solving a cubic equation or whatever, just bash it into the calculator. And definite integrals the same would apply, but we'll talk more about that. And then a real focus on efficiency. So don't write more than you need to, but always try and show you're working. Right, let's kick straight off with our first topic is this partial fractions, which is the notion of breaking up a fraction into its component parts. Just if the degree of the numerator is higher than the degree of the denominator, we must first do the division by inspection. This is a very similar process to finding oblique asymptotes, which we'll get to a little bit later on. So by inspection, I can see that I need to multiply this denominator by x to get the numerator correct up to the, or rather down to the power of the denominator. In other words, if I multiply this stuff out, this left-hand side will be created down from the x cubes will be correct and the x squareds. In other words, down to this power. Right. And then obviously I need to work out what this piece on the end here is. And that's just my sort of remainder. So in other words, if I now divide back by the denominator, I've now converted this sort of, in a sense, top-heavy fraction into a x plus. All right, and this is the piece now that I now want to focus on, the partial fractions piece. So the next thing we do is make sure that our denominator is fully factorized. All right, and then go to our next page. The next thing is to choose our partial fractions. And there's some kind of rules that you need to remember. For every linear factor, for example, x plus 1, we have a term of the form a over x plus 1. For every non-factorizable quadratic, in other words, it can't be reduced any further, we must have a sort of a linear factor, bx plus c, over that denominator. And if we have a repeated factor in the denominator, then we need to have two instances of it. So in other words, if it's a x plus 3 squared, we need to have an a over x plus 3 squared and a b over x plus 3. Right. The next step is to identify the coefficients. And we've got this method called the cover-up method. So if we go back to our example, here we've got two linear factors, and the cover-up method will help us identify both of those. In order to find the value of a, we cover up the x plus 1 over here, and we put into the remaining pieces the value of x that would make this denominator 0. So in other words, we're going to substitute in -1. Right, and we get a equals 1. Likewise, now if we want to find the value of b, what we do is we cover that up and we put in -6 into the remaining instances, and we get a value of b equals 4. So our partial fractions are as follows. You might remember that this particular question had a kind of plus x, so one would actually need to include that if one was doing this question from the beginning, the original question I showed. Right, I'm going to show you another method because the cover-up method doesn't always work. It does work with linear factors. It's a method called equating coefficients. So what we do is we now add these two fractions, and this is what we get, and then we rejig it, factor it out so that we've got kind of an x term and a constant term. And that needs to match the original numerator. So in other words, a plus b over here must equal 5. And 6a plus b must equal 10. And then we solve those simultaneously, we get exactly the same answer as before. Right, so when you have a repeated factor or a non-factorizable quadratic, the cover-up method will only be partially useful, pun intended. We will need to equate coefficients to complete the sum. So you do need to know this method as well. All right, we're going to move on to absolute value. And basically the absolute value function is defined as returning x if the input is bigger than or equal to naught, and negative x if x is less than naught. And this is a picture of the graph of it. So for example, absolute value of 2 would just be 2, but the absolute value of minus 3 would be positive 3. So a really straightforward function. Obviously absolute value of 0 just be 0, because that falls in this part of the definition over there. All right. So if we were to ask you to draw a graph such as this one, a crucial sort of thing to identify is at what value will the inside here change sign? In other words, when would it be 0? And that's obviously at minus 3. Because if x is bigger than minus 3, the stuff inside here is positive. And absolute value signs do nothing to a positive value. They actually just act like brackets. All right. So in other words, if x is bigger than minus 3, all right, or in fact equal to minus 3, this thing will just look like negative 4. All right. So it will look like, sorry, it will have a y value of negative 4, but the equation will be 2x plus 2 effectively. Right. And we can draw that. And here is, in fact, 2x plus 2. That's that piece. All right. The other piece is just a reflection across this line of x equals minus 3. So in other words, we just kind of fold it over there. One can obviously plot it as one can plot any graph by just putting in a couple of points. And remember, you only need 2 points to sort of generate a straight line. And we're looking basically for a kind of a V shape like that. Okay. So I'm just checking that I haven't left something out on this previous page. Indeed, I have. Right. So if one stops and thinks about it briefly, if we've got the absolute value of x bigger than some number, for example, absolute value of x bigger than 5, I think you can see that numbers like 6, 7, 5.1, anything bigger than 5 would work, but so would things like negative 5.2, negative 6, negative 7. So there's this kind of basic idea that if the absolute value of x is bigger than k, then x must be less than negative k or bigger than k. Likewise, if the absolute value of x is less than some fixed number k, then x must lie between negative k and positive k. Right, let's look at an example. So there one is. First step, I'm going to subtract 5 from both sides. Then what I'm going to do is I'm going to divide by negative 3. Now remember, when you divide by negative 3, a negative, you need to switch the sense of the inequality. All right, and now we've basically got this form of that. So in other words, what we now know is that 2x minus 1 must lie between minus 1 and 1. Now I'm going to add 1 to both sides and then divide both sides by 2. Right, so that's a quadratic. Sorry, not a quadratic at all. It's an absolute value inequality. Right, let's look at an absolute value equation. If we've got the absolute value of x equal to some number, for example, if we had the absolute value of x equals to 3, then clearly x could be 3 or minus 3. Right, let's have a look at how this plays out in a sort of algebraic example. When we've got variables outside the absolute value sign, exactly the same applies, but we do need to check our answers. So basically exactly this, 2x plus 3 could equal this, or the negative of this. Right, now we solve these equations, and we get our answers of 1 and 11. You can see straight away that if you put 11 in, we're going to get a problem here, because we're going to get a negative value on the right-hand side, and the left-hand side is always going to be a positive value. So in fact, 11 does not work, right? You can check that for yourself, but in fact, 1 works. So the final and only answer is x equals 1. Right, let's look at finding the absolute value of a function. So here we've got a function, and what we've been asked to draw is the absolute value of this function. Now, any value that's positive, and I'm talking about y values, will be unaffected. So for example, anything that's sort of above the axis will be exactly as it was previously. All right, and this is all summarized in the box on the left here, which I'm not going to read to you because you can read it yourself. Anything that's below gets basically made positive by the absolute value sign. So what actually happens now is that we kind of get something like, sorry, I don't think this is going very well. Maybe it is. Yeah. So I think I made a bit of a hash of that. But basically, yeah, it's not great at all. Sort of more like there, sorry. Basically, it will reflect, this this piece will reflect over. Right. If we find the f of the absolute value of x, well, the first thing we're doing now, we're finding the absolute value of our x value. So if our x value is positive, finding the absolute value of it has no effect whatsoever. So the graph for positive x values is exactly the same as it was. But if our x value is negative, all right, for example, -1, all right, -1 is a singularly bad example because it actually returns a similar value. But for example, say -1.3 or something over here, imagining that this is 1.3, the first thing that we're going to do is we're going to apply the absolute value function to, so it'll become positive 1.3, and it will then behave like the function behaved for the positive value. So what we actually kind of get a reflection of the of the positive piece across the y-axis. So in fact, and this bit no longer kind of occurs, and so nor does this bit for. So this green graph is just the absolute value of f of x, and this is f of absolute value of x. Right, we're going to move on to complex numbers and equations. Just the standard form of a complex number is a plus bi. So for example, 2 plus 5i. And remember, where I is defined to be the square root of -1, or where I squared equals -1. Okay, every complex number rather has a real part, which is that bit there, and an imaginary part, which is that bit there. Okay, to add and subtract complex numbers, you simply add their real parts and add their imaginary parts. Multiplying them is easy as well. Your calculator can do the calculations if you put it into complex mode, and it's worth taking the shortcut of using your calculator wherever possible. Right. To divide two complex numbers, what we do is we multiply the numerator and the denominator by the conjugate. Okay, and the conjugate is obtained just by changing the sign of the denominator. All right, so it's almost like a similar process to rationalizing a denominator in surds, right? And now we just conduct the multiplications. And even if the question had said you couldn't use a calculator, you can kind of use your calculator internally here a bit just to shortcut the process. Very important at the end, remember any r squareds are just -1. So this is actually 15 minus 4, which becomes 11. And then very important at the end that we do actually put it into an a plus bi form, right? Just yeah, so that's an important concept. Something that I've realized I haven't included and just occurred to me are the powers of I. The powers of I cycle through I. I squared is -1. I cubed is obviously minus I, and I to the 4 is 1. Okay, so I, -1, negative I, and then 1. And every eighth power will be 1. So for example, I to the 25, I to the 24 would be 1. I to the 25 will just be I, because they cycle. They kind of just repeat through this pattern here. Okay. Some of the Casio calculators can handle powers of I, some of them can't. So just check that you know. This is a really, really important concept, and that's that two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So for example, if you've got 2 plus bi is a minus 5i, the only way that this is possible is for a to be 2 and b to be minus 5. And these questions often involve the use of simultaneous equations. Okay, right. While we're here, just remember that a polynomial of degree n always has n roots. So for example, a cubic function will have 3 roots. A quadratic function always has 2 roots, and we know that sometimes they're equal. Something like x squared minus 4x plus 4 has equal roots, but we actually say it's got 2 equal roots of both of them being 2. All right. Okay. An important thing is that if we have rational coefficients, then both complex roots and irrational roots occur in their conjugate pairs. So for example, if 3 plus 2i is a root, then so would 3 minus 2i be. All right, and obviously x minus 3 brackets minus 2i, which is 3 plus 2i, and x minus 3 minus 2i will both be factors. Likewise for surds. All right, so here's a question which says, find in standard form a cubic function with a constant term of 870 and roots of negative 3 and 2 plus 5i. Well, if 2 plus 5i is going to be a root, then 2 minus 5i is also going to be a root. And x minus that will be a factor, and x minus that will be a factor. If minus 3 is a root, x plus 3 is a factor. And I've got an a at the front here because any cubic with these roots can be written in this form, but the a can in fact have any value. All right, and we'll still get those roots. Now what we do is a clever little trick. We just sort of reshuffle and rejig these brackets here, and you'll notice that inside now we've got a difference of squares. All right, and so this is just x minus 2 all squared minus 25i squared. Now remember, minus 25i squared is actually plus 25, right? And so that's what that comes to. We multiply that out, and now we're very, very close to the end. The question asks that we have a constant term of 870. The only way we're going to get that is if a is 10, and there we go. And if you go and solve this on your Casio calculator using the solve option 4 for a cubic, you'll see that in fact these are the roots that we get. We get minus 3, we get 2 plus 5i, and we get 2 minus 5i. And that should give you a warm, fuzzy feeling inside. Right, moving on to the natural logarithm function and e to the x. This is really not rocket surgery at all. All right, the natural logarithm function is just a log function with a base of e. So in kind of core maths, typically when we write log 5, we're actually saying that this is log base 10 of 5. And by convention, we kind of understand that. When we write ln 5, we actually understand this to be basically a log with a base of e of 5. All right, we prefer not to write it like that. This is how we write it. Our normal logarithm laws apply. These apply in core maths, although you may not use them all that much there, but you certainly would have used them in your preparation for NBTs. There's the exponent graph. It's got a base of bigger than 1. It goes uphill. And there's the natural log graph. It's got a base of bigger than 1, a base of e, and it also goes uphill. They're strictly increasing functions, both of them. Okay, let's look at a couple of questions now. Suppose we had to solve that. Well, then really what we want to do, we just want to use logs, but we're going to find the log base e. So x plus 3 will equal ln 5, natural log 5, and then x will be the natural log of 5 minus 3. Okay, here's another example. Absolute value natural log of x minus 6 equals 8. Let's add the goodness gracious me. Okay, I'm changing the question on the fly here. Let's subtract the 6 from both sides, and we get that the absolute value of the natural log of x equals 2, which means that the natural log of x could be 2 or it could be minus 2. Now I've got two separate equations to solve. Really important that you're able to take this back from log form into exponent form. So x will equal e to the 2 or e to the negative 2. All right. Okay, just the last one. This one involves a trinomial, all right? So you could be asked this in a core maths paper, but it would probably be something like 3 to the x minus 5 times 3 to the x in a core maths paper, plus 6 equals 0. And so what we're going to do is we're going to factorize it like that, and we get two possibilities, e to the x equals 2 or e to the x equals 3. And now again, we find our answers by means of the natural log function. Okay, we're going to move on to radians. The measure of an angle in radians is actually the ratio of the arc length to the radius. So that the size of this angle theta is actually S over R. All right. So in fact, the length of an arc, if the angle is measured in radians, is just R times theta. And that formula gets given to you on your formula sheet, as does the formula for the area of a sector. A sector is a piece of cake. Okay, all of this stuff's actually a piece of cake. It's just, and the area of a sector is a half times r squared times theta. Remember, theta must be in radians. And in fact, on my opening slide, I should have said one of the crucial elements for success in this subject is to have your calculator in radian mode for the whole exam. It's worth kind of being familiar with these all right? Your calculator can do the conversions for you, but I always use as a sort of checkpoint that 180 degrees is equivalent to pi radians, and then it's worth knowing your special angles in terms of those. Okay, right. A very, very common idea is to find the area of a sector, all right? And I haven't actually done an example of this here, but basically the area of a sector, sorry, not a sector, this shaded piece is in fact called a segment. All right, and the way we're going to work that out is we're just going to work out the area of the sector minus the area of the triangle. So we're just going to subtract the area of this triangle over here, and to find that area we're just going to use our normal half AB sin C, our normal area rule, but again remember that we must use the angle in radians. Okay, you need to be comfortable with the fact that we've got our reciprocal ratios. So sec theta, sorry, cosec theta is the reciprocal of sine, sec the reciprocal of cos, and cotan the reciprocal of tan. And in core maths, we only have to worry about these two co-ratios, sine and cosine, but in fact, the co-ratio of sec is cosec. So for example, if one said, what is cosec of pi by 2, which is kind of like 90 degrees, plus theta, right? We've come off a vertical axis, all right? Sine and cosec are both positive in the second quadrant. So what this will be the same as sec of theta. All right. All right. So that you need to be kind of comfortable with that idea. Okay. And then you get these identities on the data sheet, and there are sort of two new ones, and then there's no rocket surgery here either, because this one here is generated just simply by dividing every term of this one through by sine squared. So sine squared over sine squared is 1. This one over here is generated. This one over here is generated by dividing by cos squared. Cos squared over cos squared is 1. Sine squared over cos squared is 1, and 1 over cos squared is sec squared. This one comes from this one divided through each term by sine squared. Okay, and you could need to use those in solving other identities. Let's just do an example of a general solution of an equation, right? You can't do this, and this is not given on the data sheet, that cosec is the reciprocal of sine. You can't do that if you haven't learned that. So the first thing we're going to do here is turn both sides upside down, and we've now got sine of 2 theta plus that. We now find our key angle, and we know that our answers are going to be in quadrants 3 and 4, because sine and cosec are both negative in quadrants 3 and 4. And then we get into quadrant 3 by going pi, which is over here, plus a little bit, plus our key angle, or 2 pi, which is over here, minus a little bit to get into quadrant 4. Then we're not dealing with theta, we're dealing with 2 theta plus pi by 6. And from here, it's just kind of algebra, and we solve. Don't forget to say that k is an element of z. Notice that instead of adding 360k, we add 2 pi k, because remember that 2 pi is equivalent, the 2 pi in radians is equivalent to 360 in degrees. Okay. Right, we're going to move on to some limits, and this limit question in fact could be asked just in a core maths question, and it involves factorizing. All right, so there we go. Let's look at another one. This one over here, if we try and see what happens as h gets very close to 0, if we try to substitute in 0, then we get 0 over 0. There's a little trick here, and that is to rationalize the numerator. Right, and if we do that, and I'm going to go through it fairly quickly, we end up with that. All right, now the h's can divide out. All right, and we end up, in fact, as h gets very, very close to 0, this will just become like a root x, and this becomes like another root x, so we get 1 over 2 root x. And this limit that we found here is actually a first principles differentiation of f of x equals root x. We often, both in Riemann sums and in sketching rational functions, we often need to concern ourselves with limits as x approaches infinity, and that's not really in the core maths syllabus. But the trick here is to divide through by the highest power of x. Right, and the highest power of x in this question is x cubed. So if we do that, then we can see as x gets very, very large, all of these other bits are actually going to go tend towards 0. And as x gets very, very large, this expression will get closer and closer to 2/5. It's actually just, in this case, it just happens to be the leading coefficients if the highest powers are equal. Right. Something that we haven't concerned ourselves with in core maths is left and right hand limits. And so here's what we call a piecewise defined function. And for a limit to exist at a point, both the left and the right hand limits must exist. So the left hand limit is defined by how does this function behave when we approach, this is the left hand limit, all right, when we approach 3 from below. So from below, we're going to be looking at this piece. Now, as x gets very, very close to 3 from below, like 2.99999, we square it, add 1. We start getting numbers very, very close to 10. And the limit as x approaches 3 from below is 10. Similarly, this is the right-hand limit, all right? And as x gets very close to 3 from above, like 3.000000001, this is going to get very close to 7. And because those are not equal, the limit as x approaches 3 does not exist. Right, using that newfound knowledge, we are going to now talk about continuity. And continuity, the layman's definition for continuity is being able to trace a function without lifting one's pen from the page. This one is clearly not continuous at a whole number of points. All right, the formal definition is for continuity at a point A, the limit as x approaches A must exist. In other words, our left and our right hand limits must be equal and equal to one another. It's a case of the left hand knowing what the right hand's doing. All right. The function must be defined at A, and then lastly, the limit value as x approaches A must be the function value at A. Right. So if we just go and have a look at for example, at x equals 5, here the left and the right hand limits are not equal. So this one actually fails the first part. The limit at 5 does not exist. Right, so it's discontinuous at 5, and we call this a jump discontinuity or a non-removable discontinuity. Right, at 3, also at 1, the limit doesn't exist because our left and right hand limits are unequal. But in fact, the function is also not defined at 1, so it actually fails part 2 as well. All right, at 3, and in fact at -4, it's going swimmingly because the limit exists. As we approach 3 from above and below, we get 2. All right. The function's defined, f of 3 equals 3, but the limit value of 2 is not equal to the function value. It's discontinuous at 3 and in fact at -4. All right. And we call this a removable discontinuity. And it's basically removable. It's like a pothole in the road. All right. As opposed to the roads kind of not joining up. Okay, and we therefore say it's kind of removable. It could kind of be patched by reallocating this. So this, I think what I actually wanted to have here is to not have a function defined here. In other words, this would still be discontinuous because it would fail part 2. At -2, I've drawn in a dot, and the limit exists. The function value is defined, and the limit value equals the function value, and therefore this thing is continuous at -2. All right, let's move on to the concept of differentiability. All right, a function is differentiable if it doesn't have any kinks or sharp points as we kind of trace it. And here, this thing's got a kink here. All right, now, really, really important. For differentiability at x equal a, the function must be continuous at a, and the limit of the derivative from below a, the left-hand limit, must equal the right-hand limit of the derivative as we approach a. Right. So if we in fact have a look at this, all right, as we approach 2 from below, this line's got a fixed gradient, so the kind of left-hand derivative would be 2. All right. The derivative of this is 2x. So as we approach 2 from above, number is very close to 2, like 2.001. This is going to get very close to 4. And we can see that this thing actually gets steeper at that point suddenly. So it's not differentiable. All right. Okay. The sort of important little set of results is that if a function is differentiable at a point, it must be continuous. All right, we know that because that's part of the definition of differentiability. If it's not differentiable, we can't be too certain whether it's continuous or not. If it's continuous, it's not necessarily differentiable. But if it's not continuous, then we know it's not differentiable. So this sort of set of 4 results is quite important. And the function that I always use to sort of remind myself of these is the absolute value function. The absolute value function is a classic case of a function which is continuous at 0, but not differentiable at 0. Okay. All that talk of differentiability has made me keen to do some differentiation, and let's just remind ourselves about how all of this works. On the formula sheet we get these various rules, and they're the derivatives of our 6 trig functions. Remember, we only have 3 in core maths, but now we've got the reciprocals as well. Then we've got the following rules. We've got a product rule, which says that if you're differentiating a product, you differentiate the one piece of the product times by the other one, and then you differentiate the other one times by the first one. All right, and you add those 2 results. Because you're adding, it actually doesn't matter which one you differentiate first. The quotient rule says that you differentiate the numerator times by the denominator minus the derivative of the denominator times by the numerator over the denominator all squared. And then lastly, and this one is a really, really important one, to differentiate a function of a function, a composite function, we differentiate the outer function, evaluate it at the inner function, and then we multiply by the derivative of the inner function. And this can actually be nested into multiple levels, as we'll see just now. Right. The derivative of e to the x is just e to the x. Okay, and applying the sort of chain rule idea here, the derivative of e to the f of x would be just e to the f of x times the derivative of f of x. Let's tackle some examples. So this first one, x squared tan x, is just a product. So I'm going to differentiate the x squared and get 2x. I'm going to multiply it by tan x. Then I'm going to differentiate the tan x and get sec squared x, and I'm going to multiply by x squared. Right, let's see if we've got some more examples. Not on this page, we don't. Okay, this one over here is a quotient, and although it's quite innocuous, the core maths guys aren't able to actually differentiate this rather simple looking thing. But remember, we differentiate a quotient by differentiating the numerator times the denominator, and then we subtract the derivative of the denominator, which is just 1 in this case, times the numerator over the denominator all squared. There's generally not a lot of marks given in AP Maths for simplifying. So yeah, don't simplify more than you need to. And often, in fact, the question will say, you need not simplify your answers. Don't. Because if you do, I promise you won't have time. Right. This is a composite function. We've got something to the power of 7, right? And I identify the outer function by that being the second function to take place. If I was evaluating this thing, in other words, if I gave you a value for x, say x was 2, and I said work this thing out, the first thing we would do is square 2 multiplied by 3 and add 4. That's the first function. And then we would raise to the power of 7. So when we differentiate, we kind of go in the reverse order. So the derivative of something to the power of 7 is 7 of those things to the power of 6. But our chain rule says that we must now multiply by the derivative of this inside function, the inner function, which is 6x. Right. There are no more questions on that page. Let's have a look at an example here. Now, this is the chain rule again. And what we've got here is we've got, from working from the inside out, if I gave you a value for x, you would double it. Then you would find the sign, and then you'd raise to the power of 4. So the derivative of something to the power of 4 is 4 of those things to the power of 3, so 4 sine cubed of 2x. Then the next innermost function is the sine of something, and the derivative of the sine of something is cos of 2x. And then the next innermost function is just 2x, and the derivative of 2x is just 2, and I've multiplied that 2 in there. That's a very simple simplification, which is why I've done it. Okay, let's look at one last example, which just illustrates that you can actually have some of these rules sort of work in tandem. So fundamentally, this thing is a quotient, right? And we differentiate a quotient by differentiating the top times by the bottom. That's all very straightforward. And we subtract the derivative of the bottom. Now, careful, the bottom is a composite function. The derivative of the square root of something, or something to the half, is a half of that thing to the minus a half times the derivative of the inside piece. So you shouldn't be too surprised to see half x squared plus 1 to the minus a half times 2x. All of this that I'm overlining here, all right, is the derivative of the denominator multiplied by the numerator. One needs to be quite mindful in terms of keeping track of where one's at. So not a good idea to look at your cell phone or send a WhatsApp or anything while you're trying to do these questions. Right. So there's the derivative. Remember the the denominator gets squared in our quotient rule. Right. Next up, we're going to cover a concept called implicit differentiation. And basically, this is where our y is not the subject of the formula. The y's are sort of embedded in here and difficult to isolate. So what we do is we differentiate both sides with respect to x, remembering that y is in fact a function of x. All right. And then we solve for our derivative. And this is often used for non-functions, in fact, graphs and relationships that are not functions. Right, so let's have a look. This first piece is a product, x squared y. So we're going to differentiate the x squared and multiply by y. Then we're going to add the derivative of y times x squared. And that's this piece over here. The derivative of y cubed, it's our chain rule. Oh, goodness gracious me. All right, I've totally left this piece out here. The derivative of y cubed is actually 3y squared times by dy dx. All right, and then the derivative of 7x is just 7. The derivative of sine of 5y, well, the derivative of sine of something is just cos of that thing, times by the derivative of the inside piece. So 5 times dy dx. Okay, right. Now this is obviously not going to be right here. What I've now done is I've solved for dy dx. Right. So anything that hasn't got a dy dx, and take it across to the other side. In fact, this thing looks like it was probably wrong from the get-go anyway, because this should have been a minus. All right. And then I would also have, if I, in terms of factoring out a dy dx, a plus 3y squared. I hope that's now correct. Yeah, I've made this look a whole lot harder than it really is, and I apologize for that. Okay, an important application of differential calculus is what's called the Newton-Raphson method, right? And essentially what it does, it says that if we come up with an estimate for the solution, for the root of an equation, if we work out where the tangent to the curve at that point, where that hits the x-axis, that will in fact get us a better approximation of this root. And so it's an iterative repeating process. So it basically just kind of hones in. Now sometimes a function obviously has more than one root, and kind of depending on your starting value, you may identify one root rather than the other root. The question normally suggests where you start. This iterative formula is given to you on the formula sheet. Now the most important thing to remember here, and why it's highlighted, is that this formula solves f of x equal to 0. So over here, we're trying to solve x cubed minus x equals 1. It's actually the graph that's, well, x cubed minus x minus 1 is actually drawn here. So the first thing we've got to do, and we're going to use this Newton-Raphson method, but the first thing we've got to do is, in fact, to subtract 1 from both sides. We want to find out where x cubed minus x minus 1 equals 0. And it's back to this highlighted piece. We must have an equal to 0 equation. Now it's simply a matter of substituting for this particular function our values in. So on the top of the function here is just our function with xn replacing x, so f of xn, and on the bottom the derivative of this function, x cubed minus 1 x minus 1, is just 3x squared minus 1, and we evaluate that at xn. Right. Okay, and now we're ready to kind of iterate, and this is reasonably cool. So we just bring our kind of Casio calculator in here, and we're going to start off with 3 as an answer. So we say 3 equals. Right. What that does is it puts the value of 3 into the calculator's memory, which is called answer. Now what I do, right, is I type in my formula, but I don't use the number 3. I use the value answer. Answer minus fraction answer cubed minus answer minus 1 over 3 lots of answer squared minus 1. When I press equals, the calculator will do that calculation, all right, with the value of 3, and it generates the next guess. And now what I do is I just press equals, and it keeps repeating the calculation but with the new answer. It's tremendously clever, and it seems to settle about there. And then lastly, I've just got to give it to the accuracy that was asked in the question. Just before I kind of go off here, I just want to highlight this little R in my calculator, and that is for radians. Although it wasn't an issue here because we didn't use a trig function, remember radians. R for remember and R for radians. Right, we're going to move on to rational functions. As is the case with any function, we find y-intercept, the y-intercept, there will only be one for a function. By letting x be naught, we find x-intercepts, there might be more than one, by letting y be naught, and we find stationary points by letting our derivative be 0. Now, vertical asymptotes, sorry, I should have told you what a rational function is. A rational function is just a function of the form where we've got a ratio of kind of two functions. A rational function will have a vertical asymptote or asymptotes where the denominator is 0. Then, and this is a kind of mutual exclusivity thing that you'll be comfortable with from core maths probability, you can't have horizontal asymptotes and oblique asymptotes. These deal with how the function behaves as x approaches infinity or minus infinity. So it kind of can't go and approach one line and another line. It'll either have horizontal or oblique. All right, the horizontal ones are very straightforward. If we've got a higher degree on our denominator than on our numerator, then the denominator sort of dominates, is the word I'm looking for, as x gets very, very large. And so basically we'll get a horizontal asymptote of y equals 0. If the numerator and the denominator have equal powers, then in fact we want to work out the limit as x approaches infinity. And if we divide through by the highest power, as we did earlier in the limit question, we actually just see that what's really key here is that we'll just get a horizontal asymptote, which is just the ratio of the coefficients of the highest powers. Right. For an oblique asymptote, it's where we have a higher degree on the numerator than on the denominator. And so what we do is we divide by inspection, ensuring that our product is correct down to, from the highest power, down to the degree of the denominator, and the rest will be a remainder. So let's have a look. So when I look at this thing over here, vertical asymptotes at x equals 1 and minus 1, all right? Equal powers, so in fact a horizontal asymptote of y equals 3/5. Right, and that's obtained by dividing through by the highest power, in other words, by x squared everywhere, and letting x approach infinity or minus infinity. Let's have a look at another one. This one is got a higher degree on the high power on the numerator than on the denominator. It will have an oblique asymptote. It will have a vertical asymptote of x equals minus a half. Right, let's look at this oblique asymptote. So what I'm going to do is I'm going to try and generate the numerator by multiplying the denominator by something. And I need to get this right to the value of the x's. Okay, I've chosen a tricky one here. In order to get, okay, when I multiply 2x, in order to multiply 2x by something to get x squared, I must multiply it by a half x. Now I want to end up with 5x altogether. So far, I've got a half x. All right, so I need another 4.5x. But remember, whatever I put in here is going to double. So in fact, I was half 4.5, so it's 9/4. Right. If we multiply all of this out, we end up with exactly this. But we end up over here with a 9/4. And I want to end up with 1. So in fact, the remainder excuse me, is negative 5/4. All right. If I divide this back now, we can actually see exactly what is going to happen here. Sorry, that was a coughing fit, but I'm back. Right, this piece in red is not in red by coincidence. This is actually the horizontal asymptote, because we can actually see as x gets very, very large now, because remember horizontal asymptote, the oblique asymptote, not horizontal. Oblique asymptotes happen, we're interested in what happens as x gets very, very large. Well, as x gets very, very large, this piece will become increasingly small, if that's not a contradiction in terms, increasingly small, but it will basically disappear, and this will be how the function will behave for large values of x. And by large values of x, I mean x approaching infinity or minus infinity. All right, so that's our oblique asymptote. Okay, right, let's look at another example of that, because there's an interesting kind of thing that can happen. Okay, again, we've got an oblique asymptote here. I'm going to go through a very similar process. We've also got vertical asymptotes, all right? And notice here, so I've got to work out what must I multiply x squared minus 4 by in order to get this correct as far as the x squareds. And it works out to x plus 3. If I work out the remainder, and the remainder is actually that, 6x plus 6, all right, you'll now notice that if I divide through, this original rational function can be written like this. And again, this oblique asymptote is the piece in red. Right. What's interesting is that this graph, often we are taught, or people have a misapprehension that a graph cannot cut an asymptote. Sure, a graph can never cut a vertical asymptote, but in fact, graphs can cut horizontal and oblique asymptotes, but basically with those we are interested in what happens as x gets very, very large and x gets very, very small. Notice here that if x was minus 1, then this factor would disappear and this graph would actually be equal to its asymptote. So in fact, they would cut one another. All right, so we've got, you can see that over here. I've actually drawn a picture of this particular graph. We can see the two vertical asymptotes at -2 and at 2. We can see the oblique asymptote, and we can see that the graph starts approaching it as we get bigger and bigger. All right. What we can also see, though, is that the graph actually does cut at -1, as we showed over here. It cuts the oblique asymptote, and that is possible. In fact, it's not only possible; it's happened. All right. So that's an important concept. Remember, you would find these points by letting your gradient be 0. Okay. Now you'd have to differentiate. All right, using your quotient rule. Remember, though, that once you've differentiated, for a fraction to be 0, you're only concerned with the numerator being 0. So lose the denominator straight away by multiplying through by it. Okay, right. We're going to now move on to this concept of a Riemann sum, which is basically the determination of an area under a curve by partitioning it into rectangles. And obviously, the more rectangles you have, the more accurate your answer will be. Okay, and the exact area involves a limit as n approaches infinity. And we get given this formula on the data sheet. Right, so let's look at the sort of process. The first thing we do is we determine the width of each rectangle, and that's just simply, that is just simply our end, this is A, and this is B, all right? And so it's just the end point minus the beginning point divided by n. Then we generate a general xi term, which is always just, in fact, our first value plus I lots of our width. All right. Then we substitute that into the particular function that we're dealing with to get our f of xi, because we're going to need that in here. All right. And then we plug all of that into this formula, and then we separate out the sigma notations and factor out any constants, any factors which don't involve I, all right? And then we use the formulae for the sums of squares, the sums of cubes, the sums of natural numbers, and which are also given on the data sheet, all right? And then we let n approach infinity. So it's actually a fairly straightforward, although quite a tedious process. Before you even start, you can confirm your answer on the calculator, because your calculator can calculate the definite integral for you. Okay, so we're going to just go through one fairly quickly here. This is the function 2x squared minus x minus 1, and we're finding the area bounded by the curve, the x-axis, and the lines x equals 2 and x equals 4. Right, so our width is going to be 4 minus 2 over n, and our general xi term is going to be our starting point plus I lots of the width, so 2 plus 2i over n. We're going to substitute that value into our function to get f of xi, and we kind of get that as simply as we can. So we do all the sort of squaring, and right, and we end up excuse me, getting that f of xi equals that. Right, now we slot all of this stuff into the formula. All right, and now what we do is we break up these sigma notations, all right? Because the sum of some sums, you can do the sums separately. And anything that doesn't have an I in, we factor out. Now we get given formulae for the sum of 1, n times, which is obviously just n, for the sum of I, where I runs from 1 to n, and squares, etc. So you now sub in those formulae off the data sheet. And now, lo and behold, we're interested in how does all of this junk behave as n gets very, very large. And lo and behold, it actually behaves like 10 plus 14, all right, which is rather interesting. Oh, sorry, plus 16 over 3. All right, all these other terms will tend towards 0 as n gets very, very large. All right, and while I was away briefly, I just used the definite integral key on my calculator. Remember, you've got to use the alpha x as your variable. And there we get a confirmation that we've got this right. And that should give you a warm, fuzzy feeling inside as well. It's amazing how often maths can do that for you. Right, on to integration. Now, integration is both an art and a science, and it's one of my favorite topics. Don't even attempt integration before you can differentiate comfortably. This is really like trying to sort of drive a car before you can walk. Okay, so the first important idea is that we integrate a power by adding 1 to the power and dividing by the new power, plus a constant. The integral of a sum is just the sum of the integrals, and that shouldn't surprise you because the derivative of a sum is the sum of the derivatives. If we've got a constant, the integral of a constant times a function, we can work out the integral and then multiply the constant in afterwards, right? And then, I've shown you this table already, we get given a whole lot of functions and their derivatives. Right, an integral is an antiderivative, all right? So what we've basically got here now is that if the derivative of sine is cos, then the integral of cos is sine. The integral of sec squared is tan, etc. All right, so let's have a look at a first example. All right, and I lost my screen shade, so I'm just going to scroll now. But what I'm going to first try and do always is just see, can I manipulate this thing algebraically into a sort of basic flat form? All right, and so it's x squared over x to the half plus 5 over x to the half. Now, notice what I've done here is I've separated the sum and I've also factored out the 5. And now I'm literally going to just apply that rule of you integrate a power of x by adding to the power and dividing by the new power. And there's our final answer. Right, let's have a look at another example. And I like this idea of look before you leap. Before you dive headlong into integration by parts or substitution or some fancy thing, just have a careful look at the thing. Right, if you've taken time to familiarize yourself, you'll recognize that this is actually the derivative of a function, or pretty close to. Right, what I'm going to do is I'm going to take out a minus 5, because in fact negative cot x cosec x, if I was to jump back to here, you'll actually see that over here. And so that's actually the derivative of cosec x. So the integral of this thing is actually going to be just cosec x. Okay, look before you leap. Okay, unfortunately, we don't have a product rule for integration in the same way that we have a product rule for differentiation. There are two useful ideas that we can use, though, for integrating products. There's this idea that the integral of a derivative of a function evaluated at a function multiplied by the derivative of the inside function, quite a mouthful, it would be that, all right? And that is fairly obvious if we differentiate back using the chain rule. So the derivative of f of g of x would be f dashed of g of x times g dashed of x. Right, so we're looking for forms like this one where the derivative of this inner function actually occurs over here. Right, and I'm just going to integrate this straight away by inspection. The integral of something to the 19 is that thing to the 20 divided by 20. All right, and if I was to go and check, and this is the most important concept, is that you can check any integration by differentiating. If I was to differentiate this, and this is where your differentiation needs to be sharp, the power comes down to the front, cancels with that power, reduces by 1. I get x cubed plus 7 to the 19, but I must multiply by the derivative of the inner function, which is 3x squared, which is exactly that. This is correct. We always have a plus c. This is called a constant of integration. Right, whenever we have an indefinite integral, we have a constant of integration. Let's look at another one. X cos of 5x squared. Well, the derivative of 5x squared is actually 10x. Now 10x isn't quite here, but I can fix for a constant by dividing out later. So the integral of cos is sine. So I'm going to take a stab at sine of 5x squared. If you differentiate sine of 5x squared, you get cos of 5x squared times by 10x. Right? I don't want 10x, I just want 1x. So in fact, I'm going to need to divide my answer by 10 plus c. 'All right, let's go to another one. 5x squared. Well, the derivative of 5x squared is actually 10x. Now 10x isn't quite here, but I can fix for a constant by dividing out later. So the integral of cos is sine. So I'm going to take a stab at sine of 5x squared. Times by 10x. Right? I don't want 10x, I just want 1x. So in fact, I'm going to need to divide my answer by 10 plus c. All right, let's go to another one. right? This is 5x plus 3 to the half, but in fact, the derivative of the inside piece is just 5. Right, I can fix for the 5. So I'm going to write it as to the half. The way I integrate a power to the half is I add 1 to the power, and I divide by the new power. Right, so I'm going to basically have 5x plus 3 to the 3 over 2 divided by 3 over 2, which is the same as multiplying by 2/3. However, if I differentiate this result, it would be 5 times too big because of this 5. So I've got to divide by 5. This 15 on the bottom here has come from the 5 and the 3. Okay. Right. I'm going to show you another case where the sort of product rule idea occurs, and that's in integration by parts. We get given this rather fancy formula, which basically says that the integral of a product of this form can be worked out like this. And it's an interesting formula because we're trying to integrate something and we end up having to integrate something else, hopefully something better. Right. So the key thing here is to decide which thing is going to be f that I will easily be able to differentiate and which thing is going to be g that I'll easily be able to integrate. We also would like for the f to get simpler as we differentiate it. That will help us in our choice. So over here, what I'm going to do, I could integrate either of these things actually, and I could differentiate either of them. But in fact, when you differentiate x, it becomes simpler. So I'm going to let x be f of x and g dashed of x be x plus 3 to the minus 3. Now, for my formula, I'm going to need to know what g of x is. So I'm going to need to integrate this thing, and this is just a kind of composite functions, and the derivative of x is just 1. So in fact, that's the integral of that. To get from g dash to g by integrating, and the derivative of f is just 1. Now I plug these things into this formula. So I'm going to get f times g, all right? And f is just, okay, I've made an error here. Here's g. F is just x, so there should be an x over here, minus the integral of f dashed, which is 1, times g. And now I've got my integral there. Okay, I've got g there. Now, what I'm going to do on the next line here is I'm actually going to, I haven't actually shown that, but I've taken you can take the minus half kind of outside here, all right? And then we integrate x plus 3 to the minus 2 by adding 1 to the power, dividing by the new power, right? And the combination of all of that ends up with a negative back over here. You might want to just try and do that yourself, but I hope I've got it right. Be aware that there should be an x there. Let's look at another example. So I'm just trying to see if I've got another example of this I have here. X cos x, right? I can quite easily differentiate or integrate either of these, but again, if I differentiate x, it simplifies. So I'm going to let f of x be x and g dashed of x be cos x. The integral of cos x is delightfully straightforward. It's just sin x, and the derivative of x is just 1. Again, I'm going to plug them into the formula, which says that the answer is going to be f of x times g of x, in other words, x sin x, minus the integral of g of x times f dashed of x. So that's that. And now I've got to integrate sin x. And remember, the integral of sin x is actually negative cos x. Final answer of x sin x plus cos x plus c. If you're bored and short of friends, or I'm sure you're not, but if you just have a bit of time, try differentiating this, remembering that this is a product. And lo and behold, you'll see you get back to that, which will give you a warm, fuzzy feeling inside, like when you see a butterfly on a flower. Right, onwards and upwards. Okay, we're going to look next at a technique called substitution. So this is interesting. So we've got this rather messy looking thing here, but if I was to let u equal x plus 3, all right? Now, I need to replace all x's that are in here, okay? So if u equals x plus 3, then x is u minus 3. So I'm going to replace that with a u minus 3. I also can't leave dx's in. So what I do is I work out what du dx is, just by differentiating u with respect to x, and I solve for du. So in fact, in this case, du and dx are actually exactly the same. So I now write this out again, but instead of writing x, I write a u minus 3. Instead of writing x plus 3, I write a u. And instead of writing a dx, I write a du. Now that is quite a lot simpler because I can just use some algebra to get it into that form. And then both of those integrate in a reasonably straightforward manner. And then lastly, put the x's back. All right, just if you had a definite integral here, for example, suppose this was from 0 to 2. you've got a choice. You can either leave those limits off right until the very end and then evaluate with the x's with the 0 to 2, right? Or you can, if x is running from 0 to 2, then u is going to run from 2 to 5, all right, by substituting in those values. And then you can evaluate this thing over here with the 2 and the 5. What you cannot do is have it in terms of u's with the original limits which applied to x's. So just be aware of that. Okay. Just also be aware that this particular question could have been done by looking at it like that. And in fact, this question, if you're wide awake, you might remember that we've just done on the previous section by parts. So there's often more than one way to skin a cat. Okay. Not sure why one would want to skin a cat. Right. If one has a product of sines and cosines, one can make use of these three very useful formulae given on the data sheet. So for example, if I wanted to integrate something like cos 5x, cos 4x, I could use this formula to write it into that form. All right. And remember, I can do these two separately. All right. And the integral of cos is just generally sine. The integral of cos 9x is sine 9x, but I need to divide by 9. All right, so I'm going to end up with sine x over 2 plus sine 9x over 18. Don't forget our constant of integration. Yes, I started off talking about integration saying like an art and a science. Look at these two questions. They look almost identical. But in fact, this one can only be done in kind of one way, and that is by parts. All right. This one, in fact, could also be done by parts. No, it couldn't in fact be done by parts because I couldn't integrate this piece. All right. So in fact, the only way that this one can be done is by inspection or with a substitution. I could let u equal x squared plus 3, but I could in fact just realize that the derivative of this occurs there more or less. This one I would have to do by parts. Okay. So before you start, just look at the thing. Look at the thing in reading time. So how am I going to integrate that? Okay, just a little piece, evaluating definite integrals. So basically, if you've got any antiderivative, in other words, it doesn't matter what your constant value is, you just, f of x is an antiderivative, you just subtract the antiderivative evaluated at the bottom value from the antiderivative evaluated at the top value. So subtract this one from that one. Okay, so let's have a look as to how we lay this out. So an antiderivative of 2x is just x squared, and an antiderivative of 3 is just 3x. Both of them could have constants. We don't worry about constants when we've got definite integrals because they will subtract. Right, now what we do is we put 3 in, and then we subtract what we get when we put 1 in. All right, and we get a final answer of 14. Once again, any definite integral, if you can just work it out on your calculator. And so in fact, there's no need to waste the time of working it out unless the question requires it, because it involves some sort of problem solving or whatever it might be. But use your calculator wherever you can, as efficiently as you can. Okay, right. We're now going to look at area, and this is a classic case of where you can use your calculator, in fact. So the area is given by the integral, right? Just be mindful of the fact that an area that's beneath the curve comes out negative. So you can't just integrate this function x sine x the whole way from pi by 2 to 2 pi, because you'll kind of get some cancelling. So what we need to do is we need to integrate it from pi by 2 to pi, all right? And then we need to integrate it from pi to 2 pi. This piece will come out negative. Nice way of writing mathematically that we want to make it positive is just to absolute value it, all right? And we can type all of this, even the absolute value piece, straight into our Casio calculator, and we get a final answer. So don't waste time trying to work out how to integrate x sine x, all right? It would be by parts just for interest, but rather just use your calculator. Excuse me. Area between curves, what we do here is it's literally just the bigger curve minus the smaller curve, all right? So in other words, the bigger minus the smaller, right? So in this case, it's going to be from there to there. Okay, I've worked out this point of intersection of these two curves by solving them simultaneously. This is a point 14 over 3. All right, the green one, which is negative x squared plus 3x plus 2 minus the other one. You can smash this straight into your silver Casio and get an answer. Remember, areas are in units squared. Just be careful if your I should use two different color pens here, but if your functions kind of swap over, then you need to go from here to here, bigger minus smaller, and then from here to here, smaller minus bigger. All right, and you can't integrate the whole way along, otherwise you're going to get that cancelling idea again. Right, volume. There's a formula given to us on the data sheet that literally says that the volume when an area is rotated around the x-axis is just given by pi times the function value as we integrate from a to b. So the function value squared. Right, so for example, finding this, if we were to take this area and rotate it around the x-axis, we'd find its volume by integrating from 1 to 2 the square of this function. You can smash that straight into a silver Casio calculator and you get your answer. Remember, a volume will be in units cubed. Right, we're on to the last gasp, and this, I had hoped to make this video less than an hour. I have exceeded it so far already by 5 minutes. Right, but the principle of proof by induction. First thing we do is we prove it true for the first case. Normally n equals 1, but it might be n equals 3 or 2 or whatever it might be specified in the question. The next thing we do is we assume it's true for n equals k, and we use that assumption to prove it true for the next value, in other words, k plus 1. Then we conclude that the result is true from the first case onwards by PMI, the principle of mathematical induction. There typically are two sort of types. One involves proving kind of an equation, a formula, and the other involves divisibility. Let's have a look at an example of this. So first thing, if n equals 1, we check out the left-hand side and the right-hand side. They're equal to one another, so it's true for n equals 1. We've done for the first step. The second step is to assume it's true for n equals k. In other words, we write down the result with k's instead of n's, and we assume that's true. I normally put a little star next to it in order that I can refer to it later. Now I'm going to look at n equals k plus 1. So I'm going to add in the k plus first term on each side here. And I get to there. All right. What I want to now do is I want to try and write this stuff in that form with k plus 1 in place of k. Right. And it's just algebraic kind of gymnastics in a sense. Right. So we kind of manipulate it, and you can try and do this, but you'll see that ultimately we get down to there. All right. And this is just that thing with k plus 1 replacing k. All right. So just to make that clear, here we had a k plus 2. Now we've got a k plus 1 plus 2. All right. I could even be a little bit more explicit and write it as 4 minus k plus 1 plus 2. All right. And on the bottom, we've got 2 to the k plus 1 minus 1. Right. So this is exactly the same as that. All right. This is exactly the same as that, but with a k plus 1 where there was a k. All right. So if it's true for n equals k, we've proved it true for n equals k plus 1. So therefore, it's true for n equals k plus 1. And by the principle of mathematical induction, it's always true. Okay. The next type is the sort of divisibility type. And again, the first step is to show that it's true for the first case. And here we talk about natural numbers. So the first case is 1. If we put 1 in here, we get 39, which is clearly divisible by 13. Now we're going to assume it's true for n equals k. And the way I like to do this is I say, let this thing, when we put k in for n, let it equal to 13p, where p is a natural number. In other words, this thing divides it exactly by 13. Right, now we consider when n equals k plus 1. Right, and so we're looking at this thing. And again, it's sort of just manipulation. But basically, I'm going to factor out a 3 here. Right, I can't divide out a 3 because this is an expression. Right, so, and now I know from my assumption, I know that this can be written as 13p. Right, so I actually get 39p, and 39p is clearly divisible by 13. I've sort of shown that over there. All right, and therefore it's true for n equals k plus 1. And therefore, by the principle of mathematical induction, it's true for n an element of n. All right, and the question is that the end? No, it's not really. It's just simply the beginning of the end, because your real preparation for this subject should be in doing some past papers. All right, all the best.